Okay, we are going to try and finish up 13. Well, we are going to finish up 13.8 and 13.9. And then I'll start looking at some of the problems, homework stuff. Sorry if you did go and watch the video from last class. I think the reason why my pin was lagging was because of the settings were wrong on the video capture, and it was trying to compensate for the setting being the way it was. So yeah, it came out real small and real bad, and so everything's back to normal here, I hope. And yeah, as I say that and click and nothing happens. All right, so we did make it to at least talking about Stokes' theorem, right? We said we were going to just introduce the idea. We had seen in the past that, you know, what a line integral took for us to compute a line integral, right? We had to find the parametric equations for the curve C that we were going to integrate over. And then once we found the parametric equations, we would plug that into our vector field. We would dot it with the derivative of our vector function, and we'd evaluate it. Unless it was a closed curve, right? And it turned out to be, what was the great case when we could do this very easily? If this F was what type of vector field? Conservative, right? If we could show that that F was a conservative vector field and this was a closed curve, then all we'd have to do, or I'm sorry, it didn't even have to be closed, just evaluate at the endpoints, right? If it was closed, the answer would be 0, but that was the great case. But this is what it took for us to do that, right? We had to find a parametric equation for the curve. Well, Stokes' theorem tells us that that line integral over that curve of that vector field can also be found by using a double integral, a surface integral. But instead of doing the surface integral of f, you do the surface integral of the curl of f dot ds. And that is the same as this, okay? That's just from the definition of surface integrals. You can do the, does everyone agree that the curl of f is a vector field? Right? F is a vector field. Curl of a vector is a vector, so we get another vector field. And the curl is this, yes. So here's the curl. The curl is the cross product of del and the vector field, which comes out to be that. So here's our first example. This is in your notes, right? I don't need to rewrite this problem. So let's go after this. We are trying to find, we are trying to find this, but we are going to use Stokes' theorem to do it. Now let's see why Stokes' theorem is a good choice here. We have a tetrahedron, right? That's all they give us, is that our path C is this triangle that connects these 3 points, like this. So C is in black there, right? And I'm just going to orient C like this. Right, they don't give us an orientation, do they, in the problem? Like they don't tell us you're going from this point to this point to this. They just said it's the triangle. So our path C could be either direction. Now the vector field they give us is the vector field x plus y squared, y plus z squared, z plus x squared. So Stokes' theorem says again, that instead of doing the line integral over the curve C, we can do a double integral over S. Now, what's S here? S is a surface, right? But what surface? The surface bounded by our curve, right? When we draw that curve, the triangle, it creates a surface. That surface is this little portion of this plane here. So let me kind of shade that in. It's just this part here. This is not solid, right? It's not a solid tetrahedron. It's just one of the faces of the tetrahedron. And we will call this S. Now, in order to do this properly, remember with surface integrals, we had to orient which way we want our normals to point. Yes? For Stokes' theorem to work for us, what we need is to orient it so the normals are coming out of the plane, okay, kind of to the right, not into the tetrahedron. They're coming out. Now, the reason I'm doing that is because if I'm going to go along this curve, right, counterclockwise, I want my surface to be to my left. I want the normals to be coming up out of that surface. So in general, it would be more like this. If you have a curve in three-dimensional space and you're going like that, then you want your normals to come up like this. So as you look to the left of the, if you're traveling along this, as you look to your left, kind of like a right-hand rule, as you look to your left, you should see normals coming up. As opposed to this, if I had my normals going down like that, then here's the point on the surface, okay? If I am traveling here, I look to my left, I see that point on the surface and the normal's pointing down. That's not what I want, okay? All right, so I can apply this theorem to this surface. The thing that I'm going to have to do, right, in order to be able to do this problem, well, maybe we should appreciate why Stokes' theorem is good here before we actually do it. What would it take to do this without Stokes' theorem? I'd have to break this up into 3 line segments, and I'd have to do the line integral over each of the 3 segments, which maybe is not too bad, but maybe it sucks. Look at the vector function. This vector function isn't very nice, and so you'd have to plug in whatever the parametric equation was for this line segment in here, and then dot that with your derivative, and it could just really wind up being ugly. So let's start out by getting the curl of F. Just see what it looks like. Curl of F is partial with respect to x, partial with respect to y, partial with respect to z. I'm doing the, remember there's like that ijk up there? I'm not writing it down. And then I put my pieces in here, x plus y squared, y plus z squared, z plus x squared. And now do your cross product here. So I'm going to cover up this first column, right, to get my I component. What will that be? So cover this up, do this partial, not times, really, you're doing the partial with respect to y of this, which is 0. And then you're doing minus partial with respect to z of this, which is negative 2z. Now we cover up the middle one, and we do partial with respect to x of this, which is 2x, but then opposite, so negative 2x. And then still covering up the middle, partial with respect to z of this, which is 0. So we don't need to really even worry about it. And then cover up the last one, partial with respect to x of this is 0. And then partial with respect to y of this, and then subtracted, so negative 2y. So my curl is just negative 2z, negative 2x, negative 2y. Okay? Y'all agree with this? Now let's talk a little bit about last class, now that we have this curl. If we want to do a surface integral, right, of a vector field. Now don't worry that it's the curl of F. We could call this this now, this curl of f, it's just a new f, isn't it? It's just a new vector field, and that new vector field is this one down here. I don't want to call it f because it's not f, but please understand it's like we're starting a brand new problem, and we're trying to compute this surface integral. Our vector field is this, okay? Now, how do we do vector fields, surface integrals on vector fields from last class? Well, we had a formula for it, right? It's surface integral over vector fields, flux, right? And we have a way of doing it. It requires us doing, we dot f, which for us was this. We dot that with the cross product of the partial derivatives of our parametric equations for the surface, which means we would need the parametric equations for this surface. Agreed? However, we were also told that there were special cases. If your surface could be looked at as a function of two variables, right? If one of the components could be a function of two variables, then you had those three special formulas I gave you. And remember, I had to correct that one to get my normals to point the right way? Okay, so tell me, is this blue surface here, can you look at it as a function of two variables? Well, that's a plane, isn't it? Right? In a plane, the equation of a plane has x, y, and z in it. So you could solve it for, let's say, z. And so the z component would be a function of x and y. Agreed? Now, how would you find the equation of this plane? Take some points, right? Maybe take this point here, a vector going from there to there. I'm sorry, from here to here. A vector going from here to here. You take those, you cross those. That's the normal vector of your plane. And then you plug in x naught, y naught, z naught, which you could plug in what? 1, 0, 0, that point right there. Now, I've already done that work, okay? And I'm just going to write it down up here. This surface has the plane equation of x plus y plus z equals 1. And therefore, you could solve it for z and get 1 minus x minus y. Right? In other words, z is a function of x and y. Yes? Now, go to your notes, and this was note 13.7.8, right? 13.7.8. We are in the special case, the first special case, right? So because of that, I can turn this double integral over S of the curl of F dot ds into the double integral over D of negative P, right? Partial G with respect to X minus Q, partial G with respect to Y plus R dA, right? Everyone got that? Off of this? Okay. What's P for us? Yeah, be careful. This is our P, this is our Q, this is our R, right? We're not going back to the original F. That's the big thing here. I don't want you going back to the original vector field. Stokes' theorem says that you're going to be working with the curl of F as your vector field when you do the surface integral. So what is negative P for us? 2z. What is the partial of G with respect to X? So come look up here. Remember, this was our G of x, y equals 1 minus x minus y. What's the partial of G with respect to X? Negative 1, so I'm going to multiply that times negative 1. Then I'm going to do, what's negative Q? 2x, so plus 2x. And then times the partial of G with respect to Y, which is negative 1, right? And then plus R, and R for us was negative 2y. So minus 2y. all of that dA. Questions? This is would you like to pull out a 2 or just a -2, or what do you want to do? Leave it? I'm going to pull out a -2. I'm not going to give you all the choice. I'm just going to pull a -2 out. What would I be left with? X plus y plus z, right? X plus y plus z dA. Now, can I start integrating that? Yeah, see, the z is in there, right? A double integral, I can only be working with 2 variables here. And the variables I'm going to be working with are x and y, right? Z depends on x and y. So I can replace that z with 1 minus x minus y. That comes back from up here, right? We said what z was way up there. And when we do that, what do we get? We just get 1. -2 double integral over d, right? Does everyone understand that's going to be 1 minus x minus y, and that it'll cancel out the x and y, and then you just are left with the 1? And so we just have 1 dA. Now what? What's your region of integration here? You have to come back up here and take a look at this tetrahedron here. Right? Our variables are x and y, aren't they? And that means the shadow on the ground is that little triangle on the ground there, isn't it? I need to know what the restrictions on x and y are for that little triangle on the ground. Okay, so yeah, do we need to draw it, or are you okay with, well, I'll draw it here. This is the x, this is the y, this is the z. So what we're looking at is this triangle goes like this, right? X goes between where and where? 0 and 1. And then this is a type 1 region, isn't it? My y value is between 0 and, that line has got a negative slope, right? 1 minus x? Or negative x plus 1? Everyone agree with that? You understand where that comes from? Okay. Now, we just plug those in. So we are now at -2, integral 0 to 1, integral 0 to 1 minus x of 1 dy dx, right? And if you work that out, what would you get? Well, who knows? You get an answer, right? Total answer is -1. Now, go ahead. Well, on a test problem like this one, you're going to be going to the end of it. I mean, most of the integrations can be pretty clean, pretty basic stuff. Now, can anybody tell me where I could have avoided this part of the problem right here? Not had to do that? Not had to set up this whole thing on the side here? Yeah, what is this right here? That's the area of what? It's the area of D, right? And D is that triangle on the ground, right? What's the area of that triangle? Well, each side is 1, right? Base times height times half, so it should have been half. And if you just multiply -2 times half, you get -1. Yeah, we're in calculus, so that's the way we want to do it. We want to see that that double integral is an area of the region we're integrating over. So it's just FYI. I mean, that's a way to approach it. Okay. Okay. I want to show you a different approach to the same exact problem, because there's another way you could have approached this. We were looking at this curl of f dot ds, right? That's what we were trying to do. Now, if you go back in your notes and you look at the surface integral over vector fields, the flux, right? And not in your notes, in your formula sheets. This is equivalent to the double integral over S of curl F dot N ds, noting that this S with the vector on it is now an S without a vector, but now we're dotting a normal in here. And I'll remind you where that came from. This comes from this idea that ds right here really is, well, you know what, let me do it this way. This is double integral over d. You know what, that's going to waste time. What is a normal vector? The normal vector here. The normal vector, I want to reference your notes for this. We define the normal vector in 13.7.5. 13.7.5. So, you know what I'll do is I'll start with this. What is the normal vector? This is double integral over S curl F normal vector, but the normal vector is RU cross RV over magnitude RU cross RV, right? That's what the normal vector is. Dot ds, right? That's what that would mean. I'm talking about this one right here. Now, the way we get to our final formula is if we introduce write it this way. If I look at surface area, remember the integral for surface area? Wasn't it just this integral of the magnitude of the cross products? It's like, remember the cross product two vectors gave you the area of the parallelogram? We add up all those areas, it was surface area. So this surface area here becomes this. And then these two cancel out, and that gives us our formula, the final formula that we've been using. All right, I just want to show you how that kind of happens. But this one right here is the one I want to use right now to show you a different approach for this problem. I just don't want you to forget that this one exists. All right? So here's what I'm going to do. I would like for us to look at that tetrahedron. Look at that surface again, S, and tell me if you can establish what the normal vector is. Can you? That's right. We'd have to cross the two vectors on it, right? Cross it, and what was it? Well, what was the equation of that plane? I already told you it was x plus y plus z equals 1. Can you tell me from that what the normal vector is? 1, 1, 1, right? So right now, well, a normal, it's perpendicular. It's not normalized. It doesn't have unit length yet. This vector coming out is 1, 1, 1. That's my RU cross RV. Do you agree? Take two vectors on the surface, cross them, we get that. What's its length? So this is root 3. Okay, so I'm going to go now and bring this formula back up. I'm trying to do this. Curl F dot N ds, right? That's what I'm going to use here. Well, what's the curl? We already figured out what the curl was, right? It was negative 2 z, negative 2x, negative 2y, right? I'm going to dot that with what? The normal vector, ds. The normal vector is 1, 1, 1, isn't it? Yes? That's the vector, right? Yes, we're going to have to scale it, right, to make it an n. So this over its length, I was going to pull it out as just a constant outside, but do you want it in there or outside? Okay, I'll put it underneath. Over its length, right? This is the n. That's our n. Agreed? Now, let's pull that 1 over root 3 out, because it's a constant. And then dot those two things together. If you dot these two things together, right, don't you just get negative 2z minus 2x minus 2y? Yeah? And you can pull the negative 2 out. And you'd be left with x plus y plus z, which we already know when we plug in the z turns into 1. Agreed? ds, right? ds. See, in this formula, I have not gotten rid of this. Because, remember, how did we get rid of the ds in the previous problem? How did it become dA? We used the formula, right? The formula that we used converts that surface integral into an integral over d dA. Using this formula, we still have integral over s, the surface s, with respect to surface area. But what is the double integral over s of 1 ds? It's the area of what? Which one? S, right? Not to confuse it with d from previous problem, right? You see what I'm saying? It's not, we're not looking at the shadow on the ground now. We're looking at the actual face of that tetrahedron. Do you know the area of the face of that tetrahedron? Well, how do you find the area of a triangle? Well, a triangle in 3 space. Look, if I have a triangle in 3 space, then I just take the 2 vectors on it, right? I cross it, take its magnitude, and divide it by 2. That's how I find the area of a triangle. So what would this become? Negative 2 over root 3. What happened when we cross those two, right? We cross those two, we got 1, 1, 1. The vector 1, 1, 1. Take its magnitude, we already know is root 3, right? Divide that by 2, and we get root 3 over 2, don't we? And what's that? Negative 1. Same answer. Totally different approach. Same result. Do you see the difference, though? I mean, so just keep in mind here, this is this. That's the area of S, as opposed to the area of D in the previous problem. All right, pretty interesting, right? I like that. Moving on. My word of caution to you would just be, anytime you've got like a flat surface, whether it be a part of a triangle or a part of a circle, you've got to pay attention to when you can and cannot switch this over from double integral over D with respect to area versus double integral over S with respect to surface area. You've got to have that under control in your mind, when that's allowed, when it's not. Let's do another example. Maybe it'll come together. All right, find the line integral, right? So we're trying to do this line integral, where c is the circle, x squared plus y squared equals 16, with z equals 5. X squared plus y squared equals 16. That's actually a cylinder, isn't it? Radius 4. Goes up the z-axis, but we're fixing z at 5, which means it's a circle. So here's what my picture looks like. One, two, three, four, and then 1, 2, 3, 4, 5. Up here, got this circle up here, like that, right? And I'm going to orient it. What would be a natural orientation here? Looking from the top counterclockwise, right? Like this. Because if we look at the surface it encloses, it's a disk, and my formulas work when that disk goes up. In fact, I actually know what that normal vector is without anything, right? Don't you? What's the normal vector on this flat disk here? 0, 0, 1, right? It's just the k hat, isn't it? K hat vector. It's just k going up. That's what the normal vector would look like there. This is 0, 0, 1. So I'm telling you right now, I'm already leaning towards the second approach I just used in the previous problem, right? That's what I'm leaning towards because I know the normal vector and I actually know the area of this, right? Pi r squared. So all I have to do is dot this with the curl of the vector field, and then maybe things will be good. Understand? Okay, so let's get our vector field up here. Our vector field initially was yz, 2xz, right? Correct me if I'm wrong because I'm going off my own notes here. E to the xy? Okay. I mean, let's just appreciate this. If you had to find the parametric equations for this, right? Just to show you what it would be in case you've forgotten. The parametric equations for that curve would have been what? It would have been 4 cosine u, 4 sine u, right? And 5. That would have been the parametric equation that would have drawn that outside curve, right? Just the outside curve? Actually, you know what? I need to switch this. T. Pardon. T. And then what I'd have to do is I'd take its derivative, and then I would take, remember, to evaluate this function, the field at this vector curve, I'd have to plug in, for every x, I'd have to plug in 4 cosine t, for every y, 4 sine t, for every z of 5. So look at what this would be, right? And then I have to dot that with this derivative. Then I have to integrate that from 0 to pi. And that integral would suck, wouldn't it? I mean, think about what that integral might look like. So a little appreciation for what's going on here. Curl F is partial with respect to x, partial with respect to y, partial with respect to z. yz, 2xz, exy. And this actually doesn't turn out to be very pretty, but it's x e to the xy minus 2x, y minus y e to the xy, and then 5. That's right. Yes. We're going to take that and we're going to dot it with the normal, aren't we? When this gets dotted with the normal, because our normal is so nice, all I'm going to get is 1 times 5. right? But I want to write the formula down. We're going this over the curl of f, which is, I'm just going to say junk 2, because it's not the same as the other junk, and then 5. And I'm going to dot that with 0, 0, 1, ds. Okay, so this is here. And then, of course, this is my normal. Oh, hey, wait, I never, that's a vector pointing up, but it has to be unit length, right? Like in the last one, remember we divided by square root of 3? Why didn't I do that here? Because it is normal, right? It is normalized. It does have unit length. So just, I don't want you to overlook that. That's why I didn't account for it. Now, when I dot those, I just get 5. So I have double integral over s of 5. I'm pulling the 5 out, 1 ds, which is just 5 times the surface area of s, which is pi r squared. So 16, so 5 times 16 pi, 80 pi. Done. See how much faster that is? You know, especially if you would have noticed that you only needed that third component, then you could have like totally skipped everything except getting that 5, right? You could just focused all your attention on that and know that's all you're going to have. So do you see now in retrospect on this problem that by looking at it, you're wanting to use this as opposed to one of the other formulas, right? Could you look at this surface up here as a function of 2 variables? I mean, it would be just a constant function, right? But then what you would have to do is you'd have to take a look at what its image on the ground is. Its image on the ground would have been a circle, so you would have gone and switched over to polar coordinates. Or you would have just said, eventually you would have turned it into the area of that circle on the ground. But it's an extra step. I don't know if I'm getting too far ahead. Oh, yeah. Sorry, I didn't point that out. When you're doing this last one, you do partial with respect to x of this, right? Which gives you 2z. And then partial of this with respect to y gives you z. So you have 2z, take away z is z. This becomes a z, but because we are up at z equals 5, that's 5. Good, I'm glad you brought that up. Everyone got that? This is because z is 5. What is the magnitude of this? It's 1. That's the... Well, I mean, it's one of those things that you don't want to accidentally overlook. That's all. See, in the previous problem, when I did this vector right here, 1, 1, 1, that's fine. That is a direction vector, but it doesn't have unit length. So what I have to do is I have to scale it by its length, which is why here we divided it by root 3, but then we just wind up pulling that out. All right. Good. Are we at the last example of 13.8? We are down to our last 3 examples of the semester. So this one and 2 more. The next 2 are coming out of the next section. Okay, so we have find the line integral here. C is the curve of intersection of the plane x plus z equals 5 and the cylinder x squared plus y squared equals 9. All right. There's our vector field. Let me try and draw this. X squared plus y squared equals 9 is a cylinder, isn't it? Radius 3, like that. That's x squared plus y squared equals 9. Then I have what? X plus z equals 5? What is that? that plane, right? So it cuts it, slices it. Somehow, I'm not even going to care how it slices it. You can start plugging some values in, you know, to figure out where it happens, but that's it, right? I've got some slice of that cylinder. And that's my curve. So I'm going to orient it which way? Like this way? We want no, that's what I'm saying, right? I don't want that way, right? I'm not just like picking, like flip a coin, right? I want to make sure I'm paying attention to the way I orient that. I want my normals pointing up because the formulas that we're using, our normals are always pointing up the z-axis. If we are going to use a short formula, I don't know if we will. You're going to help me determine whether or not you want to use a formula or not. So the normals are actually pointed kind of like, it's kind of like the normals are coming off like this, right? Off that plane. They have a positive z component, but they're not straight up. So that's not k, unfortunately. Do you know what it is? It'd be the normal of the plane. Now, I didn't put the equation of the plane up here, but the plane was x plus z equals 5. Agreed? So you get 101, right? 101 is the direction, and then we want to scale it by its length. So let me just put down here, this is the vector 101. Everyone okay with that? And then if we put it over root 2, it's its length. Yes? Now, should we go and continue this like we did the previous problem? Why not? Yeah, do you know the surface area of that ellipse? Well, it's tilted, right? It's a tilted ellipse. I mean, it's a circle, so it's tilted. It's like an ellipse. And we don't have all the stuff we need to use a formula for it, right? There's a formula for the area of an ellipse, but that's not as easy as pi r squared, is it? Should we? Yeah, so maybe we should try and get this to the formula that gets us to dA, because dA is its shadow on the ground, right? And that's a circle. See the difference between the two approaches? I'm looking, here's my surface up here. Do I want to mess with that and have to figure out its surface area? Or do I want to look at its projection onto the ground, which we know, God, my picture is terrible. But on the ground, that's its shadow. And then look at that and let that be our D, as opposed to the S up here. So I like D, right? The function we're integrating. I'm not sure I caught any of what y'all are saying, but that's okay. Do I need to address anything? No? Okay. So how should I approach this then? Well, let me ask you this. Can you define the surface as a function of two variables? That blue thing, right, is part of a plane, isn't it? Now, of course, it's restricted, but the restriction on that plane is going to be my D on the ground. How are you going to be able to control D? It's polar, right? It's polar. Shadow. So let's look at this surface up here as being z equals 5 minus x, which means z is some function of both x and y. Now, even though y does not appear there, y is 0, it's still a function of two variables. So I can use that shortcut step, well, not the shortcut, the formulas, right? I can use one of those formulas. But I've got to first get this thing converted over with Stokes' formula, not F, curl F, dot ds. right? Shall we curl? The curl of f is equal to zero negative 2x y squared. Do y'all get that too? I don't have the vector field right in front of my eyes right now. What was the vector field? Is that right? Something seems off here. Oh, yes, it's not negative 2x. It's, sorry, it's x squared. I was looking at my work that I did, and I already was putting into the formula. So that's your curl, okay? That's your curl. That's our new vector field. And so this now becomes our P, our Q, and our R, and we're using the special case when Z is a function of X and Y. And when that happens, then I can rewrite this double integral, the curl of F dot ds, as the double integral over D, right, of negative, is it negative P? But what's P for us? 0? So it's all gone, doesn't matter. What's the next thing? Negative Q, which would be what is it? Negative x squared? Negative x squared, or negative x squared times partial of g with respect to y, which is 0. And then plus r, which is y squared, dA. Yes? This is now just a double integral problem. What I'm trying to figure out is what's the double integral of y squared dA, where our region D is the shadow of that ellipse down onto the ground. So my D looks like this. What's the radius? 3, right? This is D. What type of region is D? Oh, wait. Why aren't we doing, hey, let's just do the area of D? It's not 1, right? If this was just at the end of it all, if it was just 1 dA, then I would just say pi r squared, right? Unfortunately, this is the first problem we've done today where that last little piece of integral didn't have a constant in it. So I've got to actually do this one. So let me figure out how I can switch this region over to polar, right? I'm going to switch over. My x's are going to be r cosine thetas. My y's are going to be r sine thetas. My theta is going to be between 0 and 2 pi. And my r is going to be between 0 and 3. So my new double integral now, with my limits of integration, I'm going to go 0 to 2 pi, 0 to 3 of y squared, r squared sine squared theta, times r, right? Don't forget that r. I don't think y'all are ever going to forget that r. I hope you don't. dr d theta, right? And then from here, dot, dot, dot. I'm not going to take it the rest of the way. You would split that up into 2 separate integrals and multiply the answers, right? So one integral would be, antiderivative of r cubed, dr. The other one times. This one you do maybe power reduce, right? Do what? Yeah, I mean, yeah, you can do whatever floats your boat. You do it, right? I didn't get the answer on this one, so I don't know what it is. I just took it to there and left it alone. Okay, that's it. That's it for Stokes' theorem. The moral of the story is Stokes' theorem allows you to convert line integrals over vector fields to double integrals over surface area. And the area we're talking about is the area of the surface that the curve encloses. Good stuff, right? Now, I don't have any notes to hand out to you because there's really not a whole lot to explain, all right? This last theorem from 13.9, which is called the divergence theorem, is also known as Gauss's theorem. Oh, is that right? Gauss? That doesn't look right. Gauss's theorem. The book talks about it, I think, in the margin of the book. It does talk a little bit about Gauss. Is it Carl Gauss, right? It says it right there. Carl Friedrich? Okay. Brilliant mathematician, one of my favorite mathematicians. What's that? Yeah, he's got his hands in a lot. Well, he had his hands in a lot of different places. Lots of math, though. Lots and lots of math. Gaussian elimination for solving systems of equations. That's Gauss. Anyways, okay. So Gauss was able to determine the divergence theorem, and they call it divergence theorem because it involves div, the divergence. And so it says, let E be a simple solid region and S be the boundary of the surface. So if we take a solid, and I'll try and draw some pretty hard edges on it so you can kind of tell it's a solid. If we have a solid, E, right, with positive outward orientation, meaning we have normals popping out of this thing, right, popping out. Let F be a vector field with continuous partials on an open region of R containing E. So basically, the vector field is defined within the region of E. Then the following is true. I believe I messed up the formula. I did. I left an integral off. Do y'all see it on your formula, divergence theorem? Did I leave it off in? Yeah, I think. Well, the triple's okay, but the first one is supposed to be a double. Okay, so you might want to correct that. So yeah, do you see the correction on there? Add that integral sign onto your formula sheet. So if we want to find, what is this right here? What is that? That's our surface integral, right? It's our surface integral. Our flux, right? We've seen that before, our flux. If we want to do flux, which we spent most of last class doing flux, right? If we want to figure out the flux over a surface, if that surface encloses a solid, now not everything we've done flux on encloses a solid, right? But if it does, then we can convert that surface integral into a triple integral over the region, the solid that it encloses. But instead of doing the vector field F, we do its div. Now, what was the div? Do you remember what div of F is? What's div F? Div F is equal to del dot F. Del was the partials, right? So I'm basically doing partial with respect to x, partial with respect to y, partial with respect to z, times f. But what's f? We'll call f PQR again. PQR. So the div was just the partial with respect to x of r, p, sorry, plus partial with respect to y of q, plus partial with respect to z of r. And it's a scalar, isn't it? Right, when we dot, we do not get a vector, we get a scalar. So it's just, the div is like the easiest computation out of all computations to do. You just look at your vector field and take partial with respect to x, partial with respect to y, partial with respect to z, add them up, and you're done. This is just a wonderful theorem, okay? Let's see it in action. What I'd like for us to do is look back. 13.7 is the section, example 3. So I'm going to bring it up. I think it was from last class. Let me verify that. 13.7, example 3. Yep, it was the unit sphere problem. No, it was before that. Pardon. I think this was it. Yeah, example 3. Okay, so what we had was we had a vector field, remember? And we were trying to find the flux across the unit sphere of this with this vector field. So what we did is we said, okay, the flux is this, but the flux is also this if we can take the vector field and dot it with the cross of the parametric equations. And we know the parametric equations of a surface, so we found the partials, and we said, oh, remember partials, like we already did that 100 times ago, 100 years ago, so we just already plugged it in, and here it is. And then we dotted them, or no, we plugged it into the vector field here. Then we dotted those two together, and we got these three things. And then I said, you could show on your own time that, eventually these would all come out to be 0, and your total answer would be 0. But there was a good, 20, 30 minutes of work there, at minimum. And let's see how that's going to correspond to today and how much we're going to like Gauss's theorem, or divergence theorem. Okay, so first of all, our vector field was y, z, x, right? And because I'm trying to find the flux, it's double integral, right? It's the flux integral here, ds. Now, the unit sphere encloses a solid, doesn't it? And so I can use this theorem. It's going to be the triple integral over the div. Now, div f with respect to volume. So what is the div of f here? What's the partial? Here's PQR. What's the partial of P with respect to X? 0. What's the partial plus? What's the partial of Q with respect to Y? 0. What's partial of R with respect to Z? 0. And so the answer is 0. Yeah, it's the best kind of cheating there is. It's the shortest path. Now, in the book, they do an example like this, right? We triple integrate 0, we get 0, so we're done. That took about maybe 15 seconds, maybe less if I didn't talk and I just did it, right? The book does an example where they do the flux over a unit sphere, and they have a different vector field. It's a little more complicated, and they get an answer. Okay? Just so you know, I encourage you to look at, because there's not a whole lot in this section, 13.9 in the book. Their vector field that they do here, instead of it being yzx, it's zyx. Should we do that one instead? Yeah, let's do that. This seems kind of like more interesting, right? Can I just start as a new problem? And we won't take forever with it. We're doing the same thing. Flux over unit sphere, different vector field. Vector field. say it was? ZYX. Okay, so what's the div of this? 1, right? The only part that contributes is the middle part. The partial of q with respect to y would be 1. So what we're going to get is triple integral over e of 1 dv, right? But what's that? That's the volume of E. What's E? The unit sphere. What's the volume of the unit sphere? What's the volume of any sphere? 4/3 pi r cubed. R is 1 though. 4/3. You can compare that if you want to if you go to I don't know if you have your book or not, but if you do and it's sitting there on your table, if you go to, where is it? If you go to example 4 on page 814, all right, I'm just going to tell you, if you want, you can go look later. They do that problem the way I did it, you know, where I had to do the cross product and the partials and everything. They do it takes about half a page, and at the very end they get 4/3, just so you can see it, all right, before the divergence theorem. That's page 814. So look, on a test, if I ask you to find the flux of a unit sphere, or any closed surface for that matter, I'd be thinking div. You know, I mean, I'm not saying I'm going to give you a problem. I promise it's going to be div. That's not what I'm saying. But I would hate for you to invest half an hour into a problem or an hour into a problem that I intended for it to only take about a minute. You know what I'm saying? So you have to kind of have the big picture in mind here. All these formulas, they start to, like, I guess, once you have all these formulas, some of the stuff you did earlier becomes trivial. So my question to you will never tell you do it this way. It'll basically be do it and you find the most efficient way, whichever that is. So you've got to kind of understand how all these things work together. If you look at the test as, oh, this is definitely a 13.6 problem, then you're probably going to get stuck in a time with a time issue. I hope that makes sense. But okay, let's do the next one. What we're going to do is look at, oh, and I never finished working this out. I thought it would be fun for us to do in class. So let me see here. Going back to last class, after that problem, after a while, we did that one. Remember that one? Could we have done our div on that? That's solid? It's closed, right? What's the vector field? Could you have done partials on that and got div? What would your div have been here? 0, 1, and -1? 0? What was our answer here? It's pi, negative pi, so the next part of it. Well, did we ever? Hold on. I don't remember. No, we got pi. Didn't we? It was pi plus 1? Okay. I think I remember this note. Remember I said I should have been saying S1 there? Like here, I was using S when it should have been, see, here was S2. And I said, oh, on that previous one, I should have been calling it S1. Oh, there it is, right there. Okay. You see that problem now? We broke it up into 2 surfaces. We did all this crap right here. Oh, let's use that formula. It's great. But now we look at it and we say trivial, right? Yeah? Oh, isn't it great? I had these, yeah, hopefully y'all noticed that this whole semester. when I write, it tries to create its own title for the page. And I've had some in the past that have been like really vulgar things. And then when I'm sitting there and I'm printing out the notes or something, or not the notes, when I'm watching on the video, it'll be like, someone will be like, hey, why did you have, you know, hot sex over there on the side? I'm like, I did? No, that was secant X with some integral sign in front of it or something, you know. Yeah, so it's funny to watch it try its best. What does it have? Fizzy? Fizzy? Feds at 3D? It seems like we're watching, what's out? Feds at 3D. It's conspiracy. Yep. Okay, look at this one. This one from last class. We got 2 pi, and then we had to do another surface. We got 8/3, and we wound up getting, the answer was 2 pi plus 8/3, right? Okay. Now, what did it take? We broke this thing into 4 surfaces, right? And we did these integrals, and I went, oh, look, the normal vector, and oh, blah, and it worked out 0. Okay. Now let's see if we can apply the divergence theorem to this. Is this a closed solid? Yes. Now, I'm going to have to draw it again, because remember, what it was x went from 0 to 2, y went from -1 to 1, and then this was square root of 1 minus y squared? No. Where is it? Yes, it will be ugly. Yeah. Yeah. So, but I want to do it because sometimes div, you still have to work. You know, it's not always going to be 0. You know, you will have to work. But is it less work? We'll see. All right. So let's try this problem. So in your notes, or in your in the notes that I hand out, I'm actually doing 13.7, example 6, but with the divergence theorem instead. Understand? Okay, let me get to today. Okay, our vector field is x squared plus y squared, or sorry, x squared, y squared, z squared. I may as well get div now. Div f is 2x plus 2y plus 2z. That seems like a reasonable thing to have to work out, right? And that solid that I have comes out the x-axis, right? So my x-axis, let me see if that's what it looks like. X is between 0 and 2. Y is between -1 and 1. We all agree with that. Okay, and then the equation of this surface up here, that top surface, the top of the solid, I guess you could say, was z is square root of 1 minus y squared. So according to divergence theorem, the flux is going to be the triple over E of the div with respect to volume, which for us is triple integral over E of div f. I'm going to pull the 2 out. How about that? X plus y plus z dv. Now let's get our heads around this triple integral. Triple integral means x, y, z can appear in the integrand, right? That's okay to do. I just need to find some restrictions on, well, the only thing I need restrictions on are the z, right? Because the x is between 0 and 2. The shadow on the ground of this solid is a rectangle. So these are fine. It's just the z restrictions. So what's the bottom of that solid? Z is 0. What's the top of that solid? Square root of 1 minus y squared. So let's work this out. 2 integral I'll go 0 to 2, and then I'll go -1 to 1, and then I'll go 0 to square root of 1 minus y squared, and then x plus y plus z, d, z, y, and x, right? So why would I even ask you a triple integral problem on a test if I could just give you one of these, right? All right, antiderivative with respect to z. So how about we do this? Just to kind of save ourselves from writing a bunch of stuff, let's just work with just this part, and we'll come back and integrate it later, or we'll plug it back in later. The antiderivative of that is xz plus yz plus 1/2 z squared. I'm evaluating from z is 0 to z is square root of 1 minus y squared, right? Or I'm evaluating. Did I say evaluating or integrating? I don't know what I said. What is that icon? Oh. So plug in for z. This gives you what? X square root 1 minus y squared plus y square root 1 minus y squared plus 1/2 times z squared is 1 minus y squared. Yeah? Bless you. Now I'm going to integrate that with respect to y, right? So let me work on this part of it now. I'll change colors just to show you. I'm going to go from -1 to 1. I'm trying to integrate x square root 1 minus y squared plus y square root 1 minus y squared, and then plus 1/2 minus 1/2 y squared dy. I'll start from the right end here. Can you take the antiderivative of y squared with respect to y? Of course. So that becomes what out there? -1/6 y cubed. Okay, up here we just got plus 1/2 y, right? Okay, how about this one? Just a basic u substitution. U is going to be 1 minus y squared. Derivative of that is -2y. So I'm off 3/2. So what is that? 2/3. Yeah, but didn't we have to scale by half? So 4/3. 4/3. Hold on. 4/3. 1 minus y squared to the 3/2. Let's try that. If I take derivative of this, come out here, I get, oh no, it's the other way. I need, no, hold on. I need the 3 to cancel, right? I need the 3 to cancel, but I also need to cancel out, so come on. My brain doesn't want to do this simple integral here. 3/2 is 6. Is it 1/6? I think it's 1/6. What happens if I take derivative of that? 3/2 comes out, right? Sorry, 3/2 comes out and cancels out. 1/3? Yes, 1/3. There you go. So you multiply, you get half, and then when you do chain rule inside, the 2 comes out, it'll be negative, and then there you go. Okay. What about the one in front? You could do a trig sub, but let's just use the formula in the back of the book for that one. It is, but I mean, we know we could do it, right? Trig sub. It's just time consuming at this point. So if you go to the back, now the x will be out in front of all this, right? X, if you go to the back of the book and get your formula, you should get y over 2 square root 1 minus y squared plus 1/2 arc sine of y over 2. I know I'm writing that really small, sorry. And that's all in front of, the x is all in front of that. You all see that right? That's the formula from the back. Now we're evaluating all of this from -1 to 1. So let's try plugging, like I said, I didn't finish this off. So let's see if we can get the answer that we're looking for here. If I plug in 1, what happens? Okay, if 1 goes in here, right? If 1 goes right in here, I get 0. So this term's gone. If I plug 1 in right here, I get 1/2. What's arc sine of 1/2? Pi over 6 times 1/2 is pi over 12. Okay, so I should get the x in front times pi over 12. Y'all follow what I did there? Okay, now plug 1 in right here. What do you get? 0. Plug 1 in here. 1/2. 1 in here. Minus 1/6. So I have 1/2 minus a 6. Okay, that's what I get when I plug in 1. Now, when I plug in -1. Well, good news, this is still going to go away, right? That's still going to be 0. I still have the x in front. What about arc sine of -1/2? You have to be real careful here. Arc sine of -1/2. So just as a reminder, when we're looking at sine on the unit circle, we're looking at the y coordinate, right? On the unit circle, where is it -1/2? Right here, right? But the arc sine function has a restricted domain. Arc sine only goes from -pi over 2 to pi over 2. So even though that angle is really, what, 11 pi over 6, right, to go all the way around, we have to look at it as a negative angle. So -pi over 6 is what we get there. Is that okay? No? Is that? It's okay. Okay. Well, arc sine of, what we're saying is arc sine of -1/2, right? Says where on the unit, basically says what angle on the unit circle has a y coordinate of -1/2. Well, this one right here, right? Well, there's another one over here also, right? So in order to keep the inverse sine function a function, meaning that one input should give us one output, we have to cut off part of its domain. So what we do is we cut off the back half of the unit circle. And that way, for every number I give you between -1, y coordinate, -1 all the way up to +1, you're only going to have one angle corresponding to it. And for -1/2, the angle corresponding to it, you can't go all the way around because then you're going through that undefined area. You have to just go counterclockwise or clockwise, which is -pi over 6. I hope that makes a little more sense. Maybe not. Okay, so I'm going to come back down here. So plugging in, where were we? We were right here. We plugged in -1. That gave us -pi over 6. That gives us -pi over 12, right? Hearing crickets. -pi over 12. Then, let's see, we plug in -1 here. It's gone. -1 here. Get -1/2. Over here, +1/6, right? What would happen if I put all that junk together here? This right here, x pi over 12 minus a minus, so plus, that would be a what? X pi over 6? How about pi over 6x? That better? Then I have the 1/2. I'm going to add to it another half, so that's 1. I'm going to have a negative 1/6 and take away another negative 1/6. That's negative 2/6. That's negative 1/3. So I'm taking 1 and subtracting 1/3, so it's 2/3. Now I get to integrate that with respect to x, right? That with respect to x. And what were my limits? 0 to 2? Pi over 6, help me out, plus 2/3? Pi over 6x. Is that what we had or not? Yeah, pi over 6x plus 2/3. Shit, I hope this works. Okay, antiderivative of pi over 6x with respect to x is going to be pi over 12x squared plus 2/3 x evaluated from 0 to 2. Shit, this doesn't look right. Oh, okay, good. Well, maybe that'll work. But even then, we're screwed. Okay, 4 over, so that's pi over 3 here. And then over here, what do we get? 4/3? Now, all of that times 2, right? So we get the 8/3, right? Something's wrong with this right here. Let me just go back and look at it. Like I said, I hadn't worked it out. Did anyone see anything here? Did I multiply that 1/2 here? 1 here. Arc sine of 1/2. Y coordinate 1/2 pi over 6. That's pi over 12. But wait a minute, no, that's 0. Something's off. Maybe it was off in my formula I wrote down. Well, the x only goes to these two right here. Yeah, because this one went away when I plugged in 1. And then this one gave us the pi over 12. There's something off in here. I mean, we have 13 minutes. What was our answer that we had last time? 2 pi? Was it 2 pi plus 8/3? No, it was 8/3. Let's see. I know the answer that we got here was, yeah, it was 2 pi plus 8/3. We got 2 pi there, and then 8/3 on the other one. So somehow we lost something there. Okay, well, you get the idea, right? No, I mean, it should work out. It will. There's some error in there. So who wants to go find the error for me for bonus? You did? For that integral, who has the, let me double check that formula that I used. Hold on, let me see. Oh. Let's see, I'm using, it was minus, right? 1 minus. So tell me if this is right. It should be y over 2 square root of 1 minus y squared plus 1/2 arc sine of y. Ah, that's it. That's it. Okay, my bad. That's it. My problem was in my rendering of the formula here. I copied out of the back incorrectly. All right, well, look, that's good. We get to work with the signs again, and with the arc sign. That's supposed to just be y. I'll put it in blue. So it's correct based on the incorrect copying of the formula. Maybe we should have just done trig sub. So how does that change things? What's arc sine of 1? So where's sine 1? Where's the y-coordinate 1? At pi over 2. And then so this will be a pi over 4, right? And then over here, this one will become positive, or negative pi over 2, but then times 1/2. And then when I put those together, I get what? Pi over 2. And then now we come back over here, and we go, this was 2, right? This was 2. And now when I plug in, I get 2 squared, right? 2 squared, which is 4. 4 over 2, that gives me the 2 pi there. Where? Oh, yeah, over 2, yeah. So that would become pi over 4. Well, wait, hold on. Multiply. Yes. That's right, pi over 4. And then it's just pi. And then you multiply that shit by 2, and you are a happy man. That's a smile. Okay. That's the way it goes. Yeah. Yeah, I guess we can talk about the exam now. What do you want to know? I haven't made the exam yet. The midterm was made out of basically problems out of the chapter test. That's the way I made the midterm. If you go back and you look at the midterm and you look at the problems in the chapter test, some of them are exactly the problems in the chapter test. But I did not like the problems in the chapter test for chapter 12 or 13. So what I did was I asked for bonus for whoever could come up with homework problems, right? And whatever, Frank made up some shit and threw it online. Anyways, the major focus of this final exam is going to be chapter 13. You know, I mean, everything else you've had a mini exam over, right? I mean, and like this was a triple integral in here. Yeah, because 12 had what? Double integrals, triple integrals, polar, you know, I mean, that's all kind of built in now to a lot of what we're doing, right? There's like center of mass, things. I don't find myself, I mean, giving you anything where you'll have to compute a center of mass or, you know what I'm saying, mass or anything. Maybe setup of integral, but not computation where it's just to drive you nuts. So I sent out a homework assignment out of 13.7, 8, and 9, right? I would say that those problems will comprise probably 60% to 70% of the test. The rest will trickle, you know, a problem here, there from earlier in chapter 13. I don't see myself giving you anything like, you know, calculate the curl of this or, you know, find where this is incompressible and irrotational. That type of thing, no. I want to see end result, Cal 3 student, can you apply, can you find flux, can you do, you know, apply the div theorem when you need to, can you apply Stokes' theorem when you need to? You know, that's what I want to see at the end of this. Well, you get longer time for this. I'm just notorious. I always make an exam longer not on purpose. It just always works that way. So it's hard to say how many problems this will be. I don't know. I don't know. I mean, you don't want to like ask me because then you don't. You know, I haven't made them yet. I don't know how long they're going to take, and you know. We have a week, right, to prepare. Look at your homework. I mean, you got to make sure you can do all of those problems, make sure you're comfortable with them. I don't plan on deviating much from the homework. And then, of course, anything I did in class is fair game too, right? I mean, any example I did in class is something like it is reasonable to ask you on a test. Now, the bigger question is what can you bring to the test, right? So I have no problem with you bringing this formula sheet, well, formula sheets that has all the stuff from chapter 13 in it, right? Fine. You can have that. What else did y'all have with all the derivatives and integral formulas on it? Did y'all have that in here? No? Yeah. Yeah, that was Cal 2, but I thought I said in the beginning y'all could have those 6 pages. I think. Let's just do, on top of this, let's just do one sheet, front and back, with just whatever kind of random notes you want to put in there, reminders to yourself to do certain things. Nothing worked out. I mean, you know what I'm saying? Like, yeah, just kind of a guide for yourself. Remember that, you know, yeah, I mean, things that you think you would need that you consistently kind of forget about or something. All right? And other than that, I think we're good. I'm trying to find I doubt I'd find volume of the sphere. Yeah. That's two. Yeah, I don't think so. Y'all all had trouble with the spherical coordinates though, right? Right? That whole, you know, theta and phi. Make sure you look at that stuff because I mean anything that I noticed weakness in, I attack. No, I want you to make sure you've clarified that and you're okay with that. You know. Mhm. If the sphere wasn't one. Mhm. For triple, I yeah, you're talking about when we were using that div to find the flux over that unit sphere, and it turned out to be one triple integral 1 dv. Okay, had it been y in there, then yes, you would have had to convert to spherical coordinates, right? And because of that, you would have had to have included, like we normally put an r in there for polar. Well, we okay for double integrals, you put an r in, right? And you also put an r in when you're in cylindrical coordinates, which is basically just an extension of polar. But when you're in spherical, you have to put rho squared sine. Well, you might want to put that on your formula sheet. You know what I'm saying? Well, yeah, that's right. Yeah, yeah, rho squared and more, right? Yeah, go look it up. Change of variables could be on there, but again, I honestly, we did that on the mini exam. It was just, yeah, the whole thing was just to kind of get you to see how these things are developed, how you can change variables when you want to, and how you always have to take account for that determinant, the Jacobian. So, I do. Yes, and I have to just say something about the mini exams. I'll keep recording even though I don't want to. I got to number 7. And I don't know about you, but I get to the end of the semester sometimes and I'm just like, So I got to number 7, and I need to remind myself, because I'm going to do this class again in the summer, I need to remind myself not to put that number 7 on there, because it sucks to grade that, okay? I don't like grading it because it's just there's so many ways you can do it, and it's an identity. So, you should know if you got the answer or not. And you may have got it without showing certain steps. So what I did is I just threw it out. Now, I know that that's not good for some of you because you did it. So if you really, really want credit for it or something, you can come talk to me about it. But I graded it based on 6 problems, the first 6. Okay? I would not. Because remember, the goal of the mini exam was to try and push you past what was in the homework. I know towards the end, the mini exams really just became like homework the problems in the book, but like in the beginning they weren't. So, homework. What I'm going to do when I sit down to make the finals, I'm going to start looking at all the homework. I'm going to start looking at the examples I did in class. And I'm just going to start, pick my favorite 40, and that's what I'll put on the final. 40. Abdul's not here. Xavier's not here. Luke? No. Jason? Frank? I'm gonna turn off the video, okay? So if anyone has any other questions that have any value, we may not have